The chill of the late winter night clung to the iron railing of the balcony, a sharp, crystalline cold that seemed to penetrate the very marrow, yet it was this very stillness that sharpened the view above, where the black velvet of the sky was strewn with an impossible density of stars, each one a pinprick of ancient, defiant light against the cosmic abyss, so numerous they seemed like grains of diamond dust scattered carelessly across an infinite floor, and the faintest whisper of a breeze rustled the dry, brittle leaves beneath the veranda, a mere terrestrial echo against the silent, sprawling grandeur overhead, all of which served only to pull the mind outward, across the unimaginable gulfs between those distant suns, posing the persistent, haunting query that has echoed through human contemplation since we first looked up. Are there others out there, sentient beings perhaps looking back at their own tiny, blue-green spark, asking the very same question about us? This existential yearning, the hope mingled with the profound terror of solitude, finds its sharpest focus today in the pursuit of something seemingly forbidden by the very fabric of reality, the possibility of a civilization that has transcended the ultimate cosmic speed limit, breaching the boundary of light, opening pathways for interstellar journeys that currently reside only in the shimmering, ambitious realm of science fiction. To anchor this speculation, we must return to the early decades of the 20th century, a time when the foundations of physics were being dramatically recast, a period perfectly crystallized by the apocryphal yet eternally resonant anecdote of Enrico Fermi. Imagine the scene: a simple luncheon table in a bustling American laboratory, the clatter of silverware against ceramic, the aroma of strong, bitter coffee hanging in the air, and Fermi, the towering intellect whose very presence commanded attention, posing a deceptively simple question that cuts to the heart of cosmic scale: where is everybody? This query, posed amidst the mundane backdrop of a lunch break, encapsulated the Fermi Paradox, the glaring contradiction between the high probability estimates for the existence of extraterrestrial intelligence, derived from extrapolations of the Drake equation, which considers factors like the rate of star formation, the fraction of stars with planets, and the probability of life arising, and the utter, deafening silence that has greeted our increasingly sophisticated searches. The paradox breeds a profound sense of cosmic isolation, as if humanity were a solitary voice crying out in a universal wilderness, yet it simultaneously fuels the tenacious hope that perhaps they are not absent, merely invisible, perhaps operating under rules, or utilizing speeds we have yet to comprehend. The cornerstone of our current constraint, the very barrier Fermi implicitly referenced, lies with Albert Einstein's theory of special relativity, established over a century ago, a conceptual framework that redefined space and time as interwoven into the pliable tapestry of spacetime. Einstein posited, with elegant finality, that the speed of light in a vacuum, approximately 299,792,458 meters per second, is the absolute, invariant speed limit of the universe, a constant against which all motion is measured. To visualize this barrier, consider the thought experiment involving a hypothetical vehicle attempting to reach this limit. As its velocity approaches the speed of light, its relativistic mass increases dramatically, demanding an ever-increasing expenditure of kinetic energy, soaring toward infinity as the velocity approaches the speed of light itself, rendering the acceleration of any object possessing rest mass an impossibility under conventional mechanics. This natural law imposes a humbling scale upon our ambitions. Even Proxima Centauri, the nearest stellar neighbor, resides over 4.24 light-years distant, necessitating a minimum 4-year, 3-month journey even if transmitted information could travel unimpeded, a delay that magnifies the perceived emptiness of the intervening void. Yet, despair is the antithesis of scientific inquiry, and as we project forward into the imagined year of 2025, the landscape of theoretical possibility has become significantly energized, largely due to relentless exploration of loopholes within Einstein's own framework. Foremost among these speculative propulsion concepts is the Alcubierre metric, first mathematically articulated by the Mexican physicist Miguel Alcubierre in 1994. This concept offers a tantalizing workaround. The spacecraft itself does not violate the local speed limit. Instead, it remains stationary within a localized distortion of spacetime, a warp bubble. Picture the vessel cradled within this bubble, surrounded by the subdued hum of highly advanced field generators. Ahead of the ship, spacetime is contracted or compressed, effectively shortening the distance to the destination, while simultaneously, spacetime is expanded behind the vessel, pushing it forward. The craft surfs this manufactured wave, achieving an effective superluminal velocity relative to distant observers without any particle within the bubble exceeding the speed of light locally. This notion injects a palpable excitement into theoretical physics, suggesting humanity might be poised to break free from the tyranny of light-speed travel, transforming distant exoplanets from abstract points of light into reachable destinations. By the year 2025, research into realizing the Alcubierre drive has moved from purely mathematical curiosity to intensive computational modeling at institutions like NASA's Advanced Propulsion Laboratory and specialized departments at Caltech. Recent publications, such as the detailed modeling work by Elias Most and colleagues in early 2025, rigorously investigate the feasibility of generating the necessary spacetime geometry using the formalism of general relativity. The critical hurdle, however, remains the requirement for exotic matter, a hypothetical substance possessing negative mass-energy density, to create the requisite warp field. While no such bulk matter has been observed, promising developments in quantum field theory offer potential avenues. Advanced simulations from mid-2025 suggest that engineered quantum vacuum effects, perhaps exploiting the Casimir effect under extreme conditions, might allow the creation of the necessary negative energy density fields, albeit on a microscopic scale initially, drastically reducing the previously astronomical energy requirements, which, in early iterations, often exceeded the mass-energy equivalent of Jupiter. This narrowing of the energy gap between theory and potential engineering reality fosters an intense sense of breakthrough, reminiscent of the collective gasp of realization that follows a major experimental confirmation in high-energy physics. Complementing the warp drive theory is the concept of traversable wormholes, those exotic topologies predicted by the Einstein-Rosen bridge solutions to Einstein's field equations. A wormhole is, conceptually, a shortcut, a tunnel piercing the manifold of spacetime, connecting two vastly separated regions or even two different universes, allowing instantaneous or near-instantaneous transit. Envision stepping into a narrow, perhaps turbulent portal, the surrounding space contorting wildly, a dizzying passage where the very geometry of existence is rearranged, only to emerge immediately onto the shore of a star system light-years away. Theoretical physics, particularly as explored by leading figures like Avi Loeb at Harvard in their 2025 publications focused on advanced cosmological structures, posits that if highly advanced civilizations, those designated Kardashev Type 3 or beyond, exist, they might possess the means to generate, stabilize, and navigate these shortcuts. This provides a neat, if unsettling, resolution to the Fermi Paradox. They are not unreachable. They are simply using the infrastructure of the cosmos that remains invisible to our standard observational methods. However, stabilizing a wormhole against the tendency of spacetime to immediately collapse requires an influx of that same elusive negative energy matter, leading contemporary research to focus on quantum stabilization mechanisms, perhaps employing sophisticated manipulation of zero-point energy fields, a notion that lends the entire endeavor the thrilling uncertainty of a truly grand adventure narrative unfolding in real time. The search for these entities continues actively through projects like SETI, the search for extraterrestrial intelligence, which has evolved from rudimentary sky surveys into sophisticated, data-intensive campaigns. Picture the SETI Institute researchers in their dedicated facilities in California, surrounded by banks of servers humming with computational power, their focus fixed on the faint radio whispers sampled from the heavens, an endeavor demanding infinite patience. By 2025, the Breakthrough Listen initiative, significantly bolstered by private funding and leveraging computational resources unavailable a decade prior, has systematically surveyed millions of stellar systems, focusing heavily on exoplanets residing within the habitable zones of their parent stars. A compelling analysis released in October of 2025, assessing the density of intelligent civilizations based on current non-detection rates, estimated that the nearest truly technologically advanced neighbor might reside some 33,000 light-years away, a distance rendering conventional radio communication practically useless for dialogue, but which strongly implies that if faster-than-light travel is indeed possible, their presence should have been far more evident across the galaxy by now. Furthermore, the 2025 research agenda includes active work in technosignature detection beyond simple narrowband radio. For instance, Papers from November 2025 detail strategies for identifying anomalous thermal emissions, the waste heat signature, or smog, of vast, energy-intensive megastructures like Dyson swarms, which might betray the activity of a civilization harnessing the total output of its home star. Returning to the Fermi Paradox, the persistence of galactic silence in the face of seemingly plausible paths to superluminal travel forces a re-examination of the initial assumptions. One logical conclusion, deeply unsettling, suggests that if faster-than-light travel were physically accessible, the galaxy should already be teeming with evidence of colonial expansion and megascale engineering, leading some to posit that the physical constraints we perceive are, in fact, unbreakable walls, rendering the universe fundamentally lonely. Yet, counter-theories abound, perhaps more comforting to the adventurous spirit. Consider the hypothesis of self-imposed quarantine, or the zoo hypothesis, wherein advanced species deliberately conceal their existence, perhaps out of an ethical imperative not to interfere with emerging, less mature civilizations like our own, or perhaps due to a collective fear of interstellar conflict, a principle argued in various forums throughout 2025. A more exotic explanation, explored in a theoretical physics bulletin from the summer of 2025, involves the deliberate relocation of advanced civilizations to regions where the physics of spacetime afford them unique temporal advantages, for example, orbiting extremely close to supermassive black holes like Sagittarius A in the Milky Way's core. Due to extreme gravitational time dilation, a verified consequence of general relativity, a civilization positioned near the event horizon could experience millennia of subjective time while only days pass for an observer on the galactic periphery, allowing them eons to develop technology, including FTL methods, without broadcasting their presence to the wider, slower-moving galaxy. This notion instills a deep sense of awe, recognizing that the cleverest beings might not be spread out, but rather compressed into gravitational wells, maximizing their development window. The discourse surrounding these concepts spills dynamically beyond academic journals and into the broader public sphere, evidenced by the vibrant, often passionate exchanges occurring across scientific and speculative platforms like the X social network throughout 2025. For instance, a widely circulated post by theoretical physicist Peter Haig argued that even if FTL is physically possible, the sheer energetic cost or the inherent instability of manipulating spacetime fabric might mean that only ephemeral, localized breakthroughs are achievable, keeping true galactic empires perpetually out of reach. In direct contrast, commentators like Ashton Forbes often raise alarms about the socio-political implications, suggesting that the sudden acquisition of functional Alcubierre drives or stable wormhole technology would not lead to harmonious exploration, but rather an immediate, destabilizing arms race driven by existential threat models, a fear rooted in humanity's own historical patterns of conflict upon resource discovery. These digital town halls, rich with speculation and grounded in emerging data, create a vital sense of shared anticipation and apprehension regarding the technological precipice humanity currently stands upon. Beyond the physics of propulsion, the very nature of life and intelligence in the universe prompts related speculation regarding interstellar travel capabilities. If a civilization has mastered warp drive technology, their societal structure must be profoundly different from our own, likely having solved issues of long-term resource management, biological entropy, and socio-political fragmentation. The transition from a species confined to a single star system to a truly multistellar entity requires solving the great filter, the theoretical bottleneck preventing life from reaching advanced stages. If we assume they possess FTL, they have demonstrably passed this filter. Consider the implications for engineering. Stabilizing a warp bubble requires manipulating the metric tensor of spacetime with precision far beyond current gravitational wave detection capabilities. This suggests mastery over physics at the Planck scale, implying a civilization capable of building devices whose complexity dwarfs the entirety of the Internet projected across 100 galaxies. This level of advancement hints that perhaps their interstellar travel isn't about brute force rockets, but about manipulating the fundamental constants of reality itself, perhaps even achieving controlled manipulations of the cosmological constant. Further expanding on the limitations and possibilities, we must acknowledge the role of gravitational waves, which, though traveling at the speed of light, offer indirect insights into high-energy astrophysical events. The 2025 observation runs from enhanced LIGO-Virgo-Kagra networks have provided unprecedented fidelity in detecting binary black hole mergers. While these events confirm Einstein's predictions beautifully, they also serve as a stark reminder of the immense energy required to warp spacetime significantly. A civilization capable of bending spacetime for travel must, fundamentally, command energies equivalent to those released by colliding black holes, but do so controllably, on demand, a feat that places them firmly in Kardashev Type 2 territory, potentially bordering on Type 3 if they can harness the energy of an entire galaxy's worth of stellar output. The continued failure to detect any non-natural gravitational wave patterns, such as those that might accompany the rapid construction or deployment of a massive Alcubierre engine, remains a significant, albeit negative, data point arguing against the widespread use of such technology in our immediate galactic neighborhood. We should also consider information transfer across these hypothetical FTL capabilities. If a civilization can move matter faster than light, they implicitly gain the ability to send information faster than light, potentially violating causality, the principle that cause precedes effect. This is where theoretical physics often recoils, as violations of causality lead to paradoxes, like the possibility of sending a signal back in time to prevent one's own departure. If the 2025 consensus in theoretical physics holds, that general relativity allows FTL via spacetime manipulation, like the Alcubierre drive, but that quantum gravity effects prevent the creation of closed time-like curves, time travel, then FTL communication might be restricted to one-way, non-causal violating travel. You get there faster, but you can't influence the past. If, however, a civilization has unified quantum mechanics and gravity, and found a way to harness the causality violating potential, then the absence of visitors might be a form of self-preservation, a universal mandate to avoid the inherent instability of causal paradoxes, suggesting a galactic ethic rooted in maintaining the integrity of the spacetime manifold itself. The burgeoning field of exoplanetary science, driven by missions like the Transiting Exoplanet Survey satellite TESS and the unparalleled spectroscopic capabilities of the James Webb Space Telescope, continues to supply context for the Fermi Paradox. By 2025, catalogs list thousands of confirmed exoplanets, many displaying atmospheric compositions suggesting potential habitability. The detection of biomarkers, gases like oxygen, methane, or ozone in specific non-equilibrium ratios in the atmospheres of planets orbiting stars like TRAPPIST-1 or Proxima Centauri remains the holy grail of astrobiology. Yet, even the discovery of simple microbial life on another world would drastically increase the probabilistic argument for intelligent life elsewhere. If life is common, the argument shifts from why is there no one, to why haven't they arrived? The presence of FTL technology would imply that even civilizations arising on planets orbiting M-dwarf stars, the most common type, could easily bridge the vastness between them. The fact that even the closest promising candidates remain silent suggests either an incredibly slow rate of evolutionary ascent to intelligence, or that the FTL barrier, despite our theoretical openings, is genuinely insurmountable for practical engineering purposes. Looking ahead, the next decade of scientific exploration promises to either deepen the mystery or offer tangible evidence. The planned launch of next-generation extremely large telescopes, the European Extremely Large Telescope, the Giant Magellan Telescope, promises light-gathering power that will allow detailed atmospheric characterization of dozens more terrestrial exoplanets by 2035, providing statistical bedrock for astrobiological probability. If, hypothetically, we were to detect complex, artificial atmospheric pollutants like high concentrations of chlorofluorocarbons, a signature of industrialization, on a planet orbiting Alpha Centauri, the implications for FTL capability would be immediate and world-altering, forcing an urgent reassessment of the viability of warp drives or wormhole navigation. Such a discovery would transform the quiet, star-dusted solitude of the winter night into a charged, anticipatory silence, waiting for the first signal or, perhaps, the first physical arrival facilitated by those technologies we now only dream of. The entire discussion, from the quiet contemplation on a cold balcony to the intricate mathematics of spacetime engineering, cycles back to a fundamental human drive, the desire to connect, to overcome isolation. The very search for faster-than-light travel is not merely about conquering distance, It is about conquering time, about collapsing the vastness that makes the universe feel indifferent to our existence. If a civilization has mastered the Alcubierre drive, they have mastered the geometry of existence. If they utilize stable wormholes, they have mapped the hidden threads connecting reality. And if we, on our small, fragile planet, can even begin to mathematically outline the conditions necessary for such feats, as we are doing in 2025, it suggests that the knowledge required is perhaps not entirely alien, but an advanced stage of physics we have yet to unlock. The rustle of leaves underfoot, the tangible cold on the skin, serves as a necessary reminder of our grounded reality, while the silent, blazing panorama above compels us to keep pushing the boundaries of the theoretically possible, hoping that one day, the silence will break, perhaps with the faint, barely detectable ripple of a warp field passing through our own solar system, a silent acknowledgement from across the gulf that we are, indeed, not alone. The future remains open, written in the equations of spacetime, waiting for the ingenuity, or the audacity, to turn theory into transit.